Nanotechnology is moving from the realm of science fiction to reality, and in the process, these tiny technologies are offering giant opportunities. Nanotechnology and nanobots are rapidly emerging as some of the most revolutionary technologies of our time, holding the potential to transform industries ranging from medicine to manufacturing. Imagine microscopic robots, 1,000 times smaller than a human hair. They can perform intricate tasks like repairing damaged tissues, targeting cancer cells, or even constructing materials at the atomic level. These tiny machines could revolutionize how we diagnose and treat disease, engineer new materials, and address global challenges like pollution and resource scarcity. With the promise of unparalleled precision and versatility, nanotechnology could reshape the future, enabling innovations that were once only imaginable in the realms of science fiction. From the earliest days of science fiction, artificial life and robots have been a prominent theme. However, these creations were often human-like, such as Asimov's androids or Frankenstein's monster, rather than small-scale machines. They began as large advanced beings, quite the opposite of how life on Earth originated, with tiny, small microbes capable of little more than self-replication. These small machines are now seen as more complex than their larger robotic counterparts. In some ways, this perception has proven accurate. With our large bodies and tools, it's easier for us to construct objects on a macroscopic scale rather than at the microscopic level, let alone the atomic level. It was rightly assumed that building at the nanoscale would be more challenging than creating larger machines and robots. Early science fiction did not feature much nanotechnology. While miniaturization occasionally appeared, like entire civilizations existing under microscopes, these were usually just shrunken versions of larger things, akin to the Lilliputians from Gulliver's Travels. The idea of true nanotechnology, as we understand it today, began to take shape in the 1950s and 1960s. Richard Feynman's 1959 lecture, There's Plenty of Room at the Bottom, laid the theoretical foundation for constructing machines at atomic and molecular scales. Though not a fictional work, it inspired sci-fi writers to explore the possibilities of nanoscale technology. The term nanotechnology itself did not emerge until Eric Drexler's Engines of Creation, The Coming Era of Nanotechnology, published in 1986. This groundbreaking work popularized the concept and profoundly influenced both scientists and the public. In it, Drexler envisioned molecular manufacturing that could revolutionize industries, medicine, and daily life, an idea that sparked excitement and debate about nanotechnology's potential. He also introduced the now famous Grey Goo scenario, a cautionary tale in which self-replicating nanobots might disassemble everything, eventually covering the entire world in a silver sea of replicating machines. Nanotechnology encompasses more than just nanobots, though people often question whether such tiny robots are even possible. This is one example of a future technology where I'm willing to say, flat out and unequivocally, yes. That's because we already have tiny machines, cells and viruses, and most life on Earth exists at the microscopic level. In a sense, one could argue that Earth has already experienced a green goo event through the emergence of life itself. At some point, simple, self-replicating organisms arose, spread across the planet, and evolved to cover every surface, from mountaintops to oceanic trenches, even thriving in lakes buried miles beneath ice. This proliferation of life turned much of the land green, dramatically altered the atmosphere to be oxygen-rich, and even affected Earth's geology. Whether life emerged through random chance and Darwinian pressure, or through some form of intelligent design, the fact that it, and we, exist suggests that we can use our own intelligence to design similarly tiny machines, tailored for specific tasks of our choosing. At the very least, we can hijack existing microorganisms or viruses and modify them for our purposes, something we have already been doing for centuries, as evidenced by our use of yeast for baking and brewing. In fact, humans have long lived symbiotically with adapted or hijacked microorganisms, such as the bacteria in our guts or the mitochondria in our cells. This raises the question of whether humanity is truly defined by our DNA, given that many of the cells within our bodies don't carry human DNA. Nevertheless, we are well on our way to creating nanobots, and nanotechnology is already a significant part of modern engineering, from semiconductors to graphene. Our current technology makes extensive use of nanoscale engineering. It's also worth discussing the scale involved, as terms like nanoscale, microscopic, and atomic scale are often used interchangeably. However, they each represent different levels of size and complexity, with implications for how we might approach building and utilizing these tiny machines. For those curious, the word micro comes from the Greek word mikros, meaning small or tiny. It was introduced as a metric prefix in 1873 and denotes 1 millionth. A micrometer, or more commonly a micron, represents a millionth of a meter. This is slightly larger than the wavelength or size of a photon in the visible spectrum, and for that reason, it sets the limit of what you can see with a standard microscope, no matter how well it's built. You cannot resolve objects much smaller than the wavelength of light being used to view them. The word microscope has been around since the early 1600s, and the device itself is slightly older. The prefix is thus quite fitting for the scale. Milli, as in millimeter, actually means thousand in Latin, so using it as a prefix for a thousandth is reasonable. Kilo, the prefix for thousand, as in kilogram, 1,000 grams, comes from the Greek word for 1,000. Nano, on the other hand, is Greek for dwarf or very small. It was adapted as the prefix for a billionth in 1960, which is why you don't see references to nanotechnology before then. For measurements on the atomic scale, we previously used the angstrom, which is 1 order of magnitude smaller, 10 to the negative 10 meters. This unit has fallen out of favor in many circles in favor of standard metric prefixes, though it's still used a lot. The angstrom is particularly useful in scientific contexts as it corresponds to atomic scale measurements. For example, molecular bond lengths and atomic radii fall below the nanometer scale and are often expressed in angstroms. Picometers, a trillionth of a meter, are also useful at this scale, with 100 picometers equal to 1 angstrom and 1000 picometers equal to 1 nanometer. The prefix pico, meaning small amount or bit in Spanish, was adopted in 1960 along with the nano and femto prefixes. Femto is derived from the Danish word for 15 and represents a quadrillionth, 10 to the negative 15. Beyond femto are atto, which comes from the Danish for 18, then zepto and yocto, introduced in the early 1990s. These prefixes mean 1 sextillionth, 10 negative 21, and 1 septillionth, 10 negative 24, respectively, and are derived from the Latin and Greek for 7 and 8. While the femtometer scale is useful in nuclear physics for measuring atomic nuclei, and the attometer scale for subatomic particles, zepto and yocto are rarely used for distance. However, we sometimes use zeptoseconds to measure quantum timescales and yoctograms for the mass of subatomic particles. In speculative fiction, terms like femtotech and picotech appear occasionally. Although these aren't our focus today, picotech generally refers to technology built from just a handful of atoms, like the simplest molecules. By contrast, nanotech involves machines containing thousands, millions, or even billions of atoms. While biological cells and most organelles are microscopic, nanoscale refers to structures smaller than these, yet still composed of vast numbers of atoms. For instance, a strand of DNA contains about 180 billion atoms. Many viruses are in the billion atom range, and even very small viruses like the poliovirus contain several million atoms. Femtotechnology involves constructing devices using protons, neutrons, and other subatomic particles, creating technology at the subatomic scale. We'll touch on these ideas a bit more toward the end. For our purposes today, however, nanotechnology will refer to any machine at the virus scale or smaller, but still made of mundane atoms. We wouldn't expect a complete device to operate at the picometer scale. Rather, a piece of picotechnology might be a small component of a nanobot, such as a gear made from a graphene sheet with a diameter of perhaps a dozen atoms. I doubt picobots could exist, and when we discuss femtotechnology, it often involves concepts like space-time warping, string theory applications, or other exotic forms of matter. This is an important distinction because in the late 20th century, we tended to believe we could keep miniaturizing technology indefinitely, despite already knowing that atoms are the smallest building blocks and that quantum mechanics presents significant challenges at that scale. Nowadays, we are effectively working at that scale, albeit in relatively crude and simple ways, and we don't think there is much lower to go. We will examine the subatomic scale and concepts like string theory next week, and we will see that it's not really a smaller scale by much even there. To understand the limits of technology, we need to explore the physical constraints on matter and energy, but before delving into those, it's worth considering why nanotech is so desirable in the first place. I don't recall the first time I heard the term nanotechnology, probably during an episode of Star Trek The Next Generation. However, the first time I saw it used to its full potential and really began to think about it was in my mid-teens, thanks to my then favorite comic series, Doom 2099. I'd gotten into comic books after watching the X-Men animated series from the 90s and eventually picked up their cyberpunk-inspired 2099 titles, starting with X-Men 2099. This was also my gateway to the wider cyberpunk genre, but there were several other titles in Marvel's 2099 lineup that I got introduced to in a crossover event. Because of that, I wasn't initially aware that Dr. Doom was a villain, and I took to him right away. Admittedly, I tend to take the villains in a lot of sci-fi stories. In Doom 2099, Dr. Doom wakes up in the year 2099 with partial amnesia. Later in the series, he expresses surprise at how little nanotechnology is used, given its incredible versatility. He describes how it could turn garbage into diamonds or clean up oil spills to produce food. His speculation and impressive use of nanotech really sparked my curiosity. In truth, nanotechnology often goes underused in science fiction because, like teleportation, time travel, or Star Trek's replicators and holodecks, it can easily create over-the-top capabilities. It leads to questions like, why don't they just replicate entire armadas of ships, or teleport viruses out of sick people's bodies? When nanotech does appear in sci-fi, it's either heavily restricted by the author or treated like a magic wand capable of anything. This latter approach has some legitimacy, as nanotechnology could theoretically accomplish an astonishing range of tasks. However, it also has very real limitations. For example, you couldn't take a random pile of garbage and turn it into diamonds because diamonds are composed of carbon atoms, and most garbage contains only a small proportion of carbon. Today we are exploring nanotechnology, a field poised to reshape everything from medicine to manufacturing. But what if the survival of life and the rise of civilizations depends not on what they create, but on the very air they breathe? In this month's episode on the Fermi Paradox, we discuss air, and uncover how planetary atmospheres might hold the answer to why the stars remain silent, and what that means for our search for alien life. You may enjoy this exclusive episode alongside Faithless, a Sojourn audio drama following Castian Vandrick, a former Inquisitor turned fugitive heretic, as he embarks on a perilous journey through the Sanctum to uncover ancient truths and find his beloved Valendra. Featuring a stellar cast, it's an unforgettable chapter in the award-winning Sojourn series, an epic new sci-fi series set in the Tantalus Cluster, a collection of star systems adrift in the intergalactic void. Faithless in my exclusive episode, The Fermi Paradox Air, can be enjoyed over at Nebula, the creator-owned streaming platform where all SFI episodes air early and ad-free, along with tons of bonus content from myself and many other creators. Sign up at go.nebula.tv/IsaacArthur, using my code IsaacArthur to get 40% off an annual membership. That's less than $3 a month. Nebula also offers lifetime memberships and gift cards, so you can share exclusive content like Faithless and SFI's Nebula specials with friends and family. Even if you had enough carbon, there's that challenge of making a probe that's one atom wide to place each atom precisely. In situations like this, it would likely make more sense for tiny robots to construct a larger machine that could focus on manufacturing diamonds from a carbon feedstock, something we can already do today. Nonetheless, it's a good place to introduce the sticky fingers problem. The sticky fingers problem in nanotechnology refers to the difficulty that tiny machines or nanobots encounter when trying to manipulate individual atoms or molecules due to the relative strength of intermolecular forces. At the nanoscale, forces like van der Waals interactions, electrostatic forces, and even slight adhesion from moisture can cause objects to stick to the tools used by nanobots, making precise manipulation challenging. Indeed, there's a pretty strong debate on if it's not just challenging but flat out impossible to do single atom manipulations. We deep dived it a bit more in our episode on the Santa Claus machine, where we also discussed Star Trek style replicators and the limitations on 3D printer scale and speed. Single atom manipulations aren't necessary for effective nanotechnology. In fact, I would classify single atom manipulation as picotech, and any changes made to atomic nuclei as femtotech. Even handling small molecules like water, sugar, methane, or air particles falls into the picotech scale. This distinction helps highlight the difference between the two. A nanobot might repair tissue by identifying damaged DNA strands and eliminating them to prevent replication, allowing undamaged strands to replicate. On the other hand, a picobot could potentially repair the damaged sections of those strands directly. Here, the emphasis is on manipulation rather than just detection, which is worth noting. DNA strands, although long and thin, have a relatively large diameter compared to basic molecules, about 2 nanometers in DNA's case. Given that they can be up to 1 billion times longer than their diameter, DNA resembles more of a long wire or yarn than a pencil or needle, and it tends to spool up like a ball of yarn within the cell nucleus. If we could detect and repair or remove damaged DNA inside living cells, we would essentially have the key to biological immortality. There are other aspects of aging, such as plaque and waste buildups in arteries, but these are simpler problems for nanobots to address. Memory degradation over time is another issue, though few of us retain vivid memories from the distant past anyway. This could potentially be managed by other forms of nanotech, which do not have to be limited to microscopic robots. While enhanced memory storage and clarity would be advantageous, they're not critical for achieving longevity. The ability to alter, detect, and repair DNA is often seen as the holy grail for nanobots, as it would enable us to tackle aging at its roots. However, achieving this at a microscopic scale presents significant challenges, particularly in terms of visualization. Scanning for damaged sequences is already a complex task. Imagining a tiny robot with arms and a flashlight working along a DNA strand might look compelling in artwork, but in reality, it's impractical. As I mentioned, resolving an object requires a wavelength smaller than the object itself. The diffraction limit is constrained by the wavelength, divided by twice the numerical aperture of the imaging system. For simplicity, we can approximate this as wavelength divided by 2. Since the shortest visible wavelength is around 400 nanometers, visible microscopes can only resolve down to 200 nanometers, about 100 times the diameter of a DNA strand. Part of why their discovery is still in living memory. Clearly, visible light won't work here. Our nanobot doesn't need a human-like eye, and you can't make an eye or camera smaller than the wavelength it's meant to detect. The obvious solution is to build a system with a shorter wavelength, say 2 nanometers, to achieve a resolution down to a single nanometer. However, shorter wavelengths come with their own problems. Wavelength and photon energy are inversely related. The shorter the wavelength, the higher the energy carried by each photon, and the smaller the area it impacts. In the quantum realm, this is very different from our everyday experiences. If visible light is like a piece of paper drifting to land on a Lego sculpture, a 2 nanometer wavelength is more akin to a bullet, more energetic and hitting with far more concentrated force. Once you get into the range of 10 electron volts, EV, corresponding to wavelengths of 124 nanometers or shorter, you've entered the domain of ionizing radiation. This range is about 1/3 more compact than the shortest visible blue and violet light, and about 3 times more energetic. Ionizing radiation is highly damaging to complex molecular structures, affecting not just organic materials, but also robots and computer chips. These can be severely degraded by it, requiring a fairly thick shield made of dense material for protection, an approach that is impractical for tiny machines. This means you can't simply scan around with a flashlight or laser of this kind without causing damage, and shorter wavelengths leads to even more destruction. A nanobot equipped with a 2 nanometer wavelength light, would not be emitting visible light, which ranges up to 400 nanometers, or even UVA 315 to 400 nanometers, UVB 280 to 315 nanometers, or UVC 100 to 280 nanometers. While UVC is blocked by our ozone layer and is known for its germicidal and sterilizing properties, 2 nanometer wavelengths are much shorter still. This wavelength doesn't even fall within the extreme UV range, 10 to 100 nanometers, which is used in semiconductor lithography to etch tiny circuits as if with a knife or blowtorch. Instead, 2 nanometers is actually in the X-ray range, specifically the soft X-ray range, which spans from about 100 picometers to 10 nanometers. For reference, hard X-rays range from about 1 picometer up to 100 picometers. This adds another layer of complexity to the idea of a tiny robot repairing DNA strands of its own size, making direct DNA repair impractical. Vaporizing DNA, on the other hand, is quite feasible. You might wonder how this could be beneficial, especially since it's unclear whether the potentially damaged DNA is good or bad. However, there are 2 ways that DNA repair could still work in this context. First, the robot doesn't need to read the DNA to determine if it's faulty. DNA acts as a blueprint, and it's clear there's an issue if it's producing damaged cells. For perspective, cells are microscopic entities composed of trillions of atoms. If atoms are like the bricks that build a cell, then a cell is as large as a city, and DNA is a complex skyscraper within that city. You don't need to examine every brick to identify structural damage or to pinpoint and remove the problematic DNA structure. This approach is extremely advantageous as DNA replication is nearly error-free. By targeting and eliminating dangerous mutations, such as cancerous cells, you could significantly increase human lifespan or slow aging by orders of magnitude. Incidentally, we can't even engineer self-replicating organisms to reduce replication errors and become virtually mutation-free, but more on that later. Tiny robots are just one aspect of nanotechnology, and there are other ways to repair a cell, such as by inserting a DNA strand that is error-free. But where do we get that error-free DNA? Fortunately, we can print DNA. And the process is relatively straightforward. Picture a carbon nanotube, a simple structure of graphene folded into a cylinder that's as wide as a DNA strand, around 2 nanometers or 2000 picometers. With carbon bonds and graphene measuring 142 picometers, this nanotube resembles a mesh or chicken wire, as wide as your arm and potentially as long as needed to create a piece of DNA, whether it's an entire strand, a single chromosome, or even individual genes that can be linked together as they form. DNA can even be printed directly within a cell, and we already have the technology to do this at a similar or smaller scale. We also have existing organisms like viruses that can hack into cells and hijack production to use as a basis. For a conceptual example, imagine 5 nanobots labeled A, T, C, G, and X. They converge on a damaged cell, much larger than they are, while dragging a nanotube behind them. X creates a tiny opening in the cell membrane, acting like a syringe needle, and pulls the nanotube through this opening. X then locates the damaged DNA and vaporizes it, while the other 4 nanobots start delivering nucleotides through the nanotube, A, T, C, and G, or adenine, thymine, cytosine, and guanine. These nucleotides are fed into the nanotube in the precise order required to build a new DNA strand, following the correct blueprint. Each nanobot has its own reservoir of the required nucleotides and releases them at the correct time into the nanotube. I should also note that precision timing and positioning is also a hard problem in nanotech, but let's bypass that for now. As the DNA strand takes shape, X guides the newly synthesized DNA to the target location inside the cell. Carbon nanotubes are extremely useful in nanotechnology, and could likely be a primary building material for many nanobots. However, nanobots don't need to build everything themselves. We could have larger microscopic graphene or nanotube factories that manufacture components or even entire nanobots. While the idea of a universal assembler, modeled after self-replicating cells, is central to early nanotechnology concepts, there isn't necessarily a need for self-replicating robots. Indeed, I'd argue they offer less value than some alternatives while adding real risk. Instead, a larger microscopic factory could produce them, potentially made by smaller factories or even dumb nanobots that follow the instructions of a smarter and larger machine elsewhere, whether in the body, the house, or even off-site. There are certainly other ways to build DNA quickly or to enter cells. We know that viruses can penetrate cells, and that DNA replication in nature takes only a few hours, while modern DNA printing can take hours to weeks. We could improve on this, but more importantly, we don't need to make it perfect. By occasionally providing a few cells with entirely new DNA, printed from a flawless digital template, we can ensure that the body's natural processes use clean DNA, while nanobots eliminate mutated cells, or old cells if you are seeking to replace them with totally new DNA, like if you were switching out the gene for hair or eye color. Of course, there's always the concern of rogue nanobots, mutant machines rather than mutant cells. Nature often inspires our designs but does not provide rigid blueprints. We worry about scenarios like gray goo because we picture viruses or cells replicating uncontrollably. However, we need not worry as much about a simple microfactory running amok if it's only capable of making specific types of bots, and none that build, maintain, or supply itself. We can also borrow from how nature limits cell growth in us already. Nature provides us with diverse ecosystems where various organisms overlap, compete, and prey on each other. In a nanotech ecosystem, you'd have very diversified systems working together to enhance each other. Some bots might act as scouts, searching for problems like damaged DNA or tiny cracks in an engine wall or a house. Others could be resource gatherers, collecting materials from pods of encapsulated building supplies towed to the site or ingested by a person. Some bots might handle recycling or removing damaged materials. There might also be specialized scanners coordinating with others to produce real-time 3D maps, compiled by a nearby microbot tasked with maintaining positioning for all the bots. You might even have bots whose only job was to be a positional beacon for others to work off of. Another bot could serve as a fuel depot, supplying energy in the form of simple sugars, starches, or even advanced sources like carbon-14 diamond batteries. Larger bots might use wireless power, but with microwaves as our preferred energy transmission method. However, since microwaves are micro by definition, they are not suitable for powering nano-sized devices. You might have a microwave-powered sugar factory that the smaller bots came to for fuel, or where specialized bots went to pick up fuel to deliver to other bots. In this ecosystem, larger bots aren't necessarily smarter or at the top of the hierarchy. Each bot is designed to perform a specific task, and typically just that one task. In traditional nanotechnology, a universal assembler can theoretically do anything and replicate itself, but we don't necessarily need that. Such a concept might not be safe or efficient. If you want nanobots to operate far from human oversight, you need something with significant intelligence and self-replication abilities. The intelligence issue is the same with any AI. Size does not matter, and you shouldn't build anything smarter than it needs for its job. However, constant human oversight may not be required, and self-replication can be achieved through a chain of bots where each produces smaller bots. At the top, you might have a dozen larger bots, requiring agreement from these 10 of them to construct a new sibling, ensuring that a mutation in one or even two would not result in a defective copy. We've explored this concept in more detail in episodes focused on self-replicating machines and space probes, of which nanobots are a subset. As we've seen, nanobots do not actually need to be self-replicating at all. The concept of a single universal assembler that can reproduce itself and handle all functions isn't practical. With billions of them in a single human or similarly sized organism or device, it is more sensible to have thousands of specialized nanobot designs, each tailored to a specific role. You wouldn't use a screwdriver for every task, nor attempt to build another screwdriver with a screwdriver. We need a wide array of specialized tools, and even the larger or microscopic ones, those that might not fit inside cells but are still cellular sized, can be delivered in a pill or a syringe. Nanobots would likely vary significantly in size and function, with some being relatively large. This ecosystem could also include connections to macroscopic computers, like your smartphone, and even extend to the internet. On the smaller side, it's not just about miniaturizing tools like knives or pliers. These are straightforward to produce at the nanometer scale, where graphene sheets are incredibly sharp. Propulsion systems might mimic flagella-like whips or tentacles, serving dual purposes as both movement and manipulation tools without needing to be much larger. Building nanobots requires much more than just miniaturizing tools though. They need a source of motive force, an energy supply, and either enough intelligence to function independently or a transmitter for remote control by a larger, more advanced design. We've already created nanometer scale electric wires in the lab. As we mentioned in our space elevator episode last month, graphene is an excellent conductor, and its relative, hexagonal boron nitride, is a superb insulator. A graphene nanotube encased in a boron nitride nanotube could serve as an ideal electrical or communication cable, linking larger nanobots or microbots to smaller robots that may act primarily as scalpels or pliers. While nanoscale structures aren't typically known for their durability, they need only be as sturdy as biological structures to be effective. Metals could be viable alternatives if graphene and similar materials don't develop as expected, although graphene's properties are likely to revolutionize nanotechnology. In considering the mechanics of nanobots, it is useful to look at the 6 classic simple machines, which form the foundation of more complex or compound machines. These are the lever, wheel and axle, pulley, inclined plane, wedge, and screw. There's some debate on whether this list even needs to be that extensive, since a pulley is essentially a type of wheel. For a pulley to function, you also need a rope, not just a wheel and axle. As we discussed earlier regarding nanoscale wires, we are capable of constructing nanoscale ropes as well. Time and experience will determine how thick an inclined plane, wedge, or lever needs to be to perform its job, which depends on the task and the materials used. These can be built at the small end of the nanoscale, just a few atoms thick. We are already constructing circuits at this scale, though commercial production typically lags behind laboratory capabilities. Practical engineering and manufacturing may impose larger size limits than what is possible in the lab. For example, a screw, a twisted inclined plane, needs to be slightly larger, as would wheels and gears. But constructing relatively simple mechanical devices, like those used before microengineering took off in recent decades, should be feasible at tens of nanometers in scale. Some may be even smaller, while others might need to be a bit bigger. Overall, there's little stopping us from building at this scale, which reaches down to the viral scale and potentially much smaller. While it won't be an easy journey, progress is rapid, and experts in this field are generally optimistic, at least until we reach the sticky finger scale. Nanotechnology is advancing, and we already have some forms of it today. Consider it like AI. A decade ago, people spoke of AI as if it was science fiction, though basic forms were already in use. 2 decades ago, many thought AI was either impossible or would immediately lead to a technological singularity. Today, AI is a lot more mundane, but undeniably present. I'd say nanotechnology is similar, probably about a decade behind AI. The idea of tiny nanobots eliminating aging or repairing neurons damaged by life or cryopreservation may still be a long way off. But instead of viewing them as magical solutions, think of nanobots as tools in a toolbox, designed to address problems under our control and guidance. Going beyond into the true picotech scale, and even the femtotech scale, enters the realms of what we might consider magic, or more specifically what we call Clark tech, in homage to Arthur C. Clarke's famous third law: any sufficiently advanced technology is indistinguishable from magic. Constructing machines beneath the quantum scale, where objects don't even have fixed positions, but instead exist as probability distributions across space, seems like an impossible task, and I think it probably is. But we cannot rule out the possibility of pulling off tricks that defy our current understanding, like miniaturizing people, as seen in classic science fiction like Fantastic Voyage. We might one day manipulate or even forward space-time in such a way that, like Doctor Who's TARDIS, an entire macroscopic factory could be compacted into a subatomic pocket dimension, with a single entrance just a proton or electron wide, from which it could emerge to manipulate objects. Much as the microscopic realm is underlain by the nanoscopic, and below that the picoscopic atomic layer and the femtoscopic nuclear layer, there may be even deeper layers of reality that are more deterministic, potentially allowing for machinery that quantum mechanics would deem impossible. We'll explore one such possibility later this week as we delve into string theory and attempt to simplify and unravel its complexities. For now, the nanoscopic level is the limit, but it's an incredibly valuable limit. It holds the potential to solve all medical problems, offering unbounded life expectancy in perfect health. Nanotechnology could enable us to repair rather than replace our machines, fixing them with unparalleled efficiency, upgrading rather than discarding them, and building them even better, as tiny workers access microscopic nooks and crannies that were previously unreachable. This technology not only supports existing organisms, like us and our pets, by enhancing healing and performance, but also extends that capability to maintaining our inorganic creations and enabling the construction of new ones that microscopic tools simply could not achieve. Indeed, nanotechnology could be called the future of everything, not just because of all the new doors it opens, but because it will be incorporated into nearly everything, and quite possibly everybody.